Hi everyone, and welcome to this short video that is going to show how to answer these questions on radioactivity, half-life, and nuclear reactions. Okay, so we'll do a couple of questions today and we'll be able to answer anything that they will throw at us in the exam. So in this first question, they are asking about the different types of radioactive emissions. And there are three main types, the alpha, beta, and gamma. But before we could fill out this table, we should really understand a little bit about what they actually mean. Okay, so if I scroll down here, I will see some elements, right? So we know if we have an element here, so this is the element carbon, we know from chemistry that carbon is the sixth element, right? And it has a mass of 12, right? That's regular carbon. So this number here is the atomic number or the number of protons in the element, right? And we know that the number of protons determine what the element is going to be. So if it had, 7 protons, it will not be carbon, it will be something else, right? This number here is the mass number, and this is important. The mass number is made up of the number of protons and the number of neutrons, because these are what have the mass, right? So protons have a mass of 1, neutrons have a mass of 1. Usually there are the same number of protons and neutrons in an element. However, if there's a difference in the number of neutrons, the element stays the same because the atomic number will not change, but the mass number will change, and we call this an isotope. An isotope is very unstable. It means that it does not want to remain an isotope. It wants to go back to the way it was, right? Stable, which is this. This is stable, right? So therefore, this will undergo decay to become stable. So it will start to emit different particles in order to get back to the balance, for example, 6 and 12. All right? So there are three types of radioactive emissions that could happen in order to get this back. The first decay is alpha decay. The second, beta. And the third is gamma. But the gamma you don't really need to worry about the gamma that much. It's not very important in the equations that we've seen over here. Just the properties you just need to remember. But for the equations, the alpha and the beta are very important. Now I'll show you how those work just now. But now that we have the background information on the types of radioactive emissions, we could go and fill in the table. Okay, so the alpha emission has a positive charge. The beta has a negative charge. The gamma has no charge, so it's neutral. Okay, ionizing ability is how powerful these emissions are, right? So how far it could pass through different stuff and things like that, right? But what you need to know is that the alpha emission has a strong ionizing ability. The beta is kind of in the middle, so we could just say it's ionizing. It's neither strong nor weak. Right, and the gamma, it's weak. Okay, and that's how we fill out this table. These are things that you just need to know. All right, now the equations carry some marks as well, and these boxes are very easy to fill out. So as I said before, the only emissions we need to remember are the alpha and the beta. Now how do we figure out, well, which one goes in which box? Well, the alpha is essentially a helium element. Helium meaning atomic number of 2 and a mass number of 4. The beta is essentially an electron. Now if you remember what an electron is, it actually has negligible mass and it's negatively charged. So we just put a -1 there. Okay? So this is how you could remember what these are. Now, to figure out what goes in the box is just like algebra, right? So whatever in this box needs to add to this nitrogen atom here, or 14 and 7, to get back these numbers in the carbon. So let's focus on the top number first. 14 and 14. Well, they are equal already, which means in our equation we can't have anything here on top other than 0, because then it will throw off the balance, right? So therefore I already know that the answer is the beta. Why? Because the beta has a mass of 0, so that's the only one that would actually work. The helium, it has a mass of 4, so if you were to put that there, it will throw off. It will be 14 plus 4, and that's not equal to the 14 on the left hand side. Now let's take a look at the bottom number just to be sure, right? So we have 6 here, and then we have 7. So in order to get back the 6 from the 7, we need to minus 1. And what has the minus 1? The beta emission. So therefore the beta goes here. Alright, and we could actually put in the values 0 and 1 to show them that we know what we're talking about. In part 2, we have some elements here. So let's take a look at it again. The mass number, we have 226, and then we have 222. So therefore, to get back to 226, we need to add 4 to the 222. And which one has 4? The alpha. So 4 here, and let's see if the 2 makes sense. We have 88 here and 86. So 86 plus 2 will give us back the 88. And there we have it. Very simple. Okay. The next question is about half-life. So how half-life works with these radioactive decay is that the isotopes would decay by half its amount in a certain number of time. That's in a certain time. That's what we mean by half-life. So for example, this counter here, the Geiger-Müller counter, it actually counts the emissions from the isotope, right? So how many times it throws off the beta or the alpha, it will actually count, right? So our sample had an initial count of 1000, right? Now, after 15 hours, the sample starts to throw off more, so it starts to get less and less and it gets slower, right? The count rate was 250. So it went from 1000 to 250 in 15 hours. But you might be saying, well, half-life, but 250 is not a half of 1000. So how does that really work? Well, how do we get from 1000 to 250 by keep taking halves from it? We just do it. So 1000, if we start off with 1000 and we half that, we go to 500, we half that, and then we go to 250. So therefore, in 15 hours, we went from 1000 to 500 and 500 to 250. So that's 2 half-lives there. Okay, so therefore we could say that the half-life is 7.5 hours. Right, because we had 2 half-lives in 15 hours. Alright, so that's how we do it there. Okay, let's take this next question. Lithium-7 is an isotope of lithium. The mass number is 7 and the atomic number is 3. Use the information given above to determine the number of protons and neutrons present in an atom of lithium-7. So they kind of give us the answer here. The atomic number is 3, and we know the atomic number and the proton number are the same. So therefore it has 3 protons. And how do we figure out the neutrons? Well, the mass number is 7. So if we know there are 3 protons, to make up the 7, we will need 4 neutrons. 3 plus 4 is 7. Now a very easy format here. We just need to draw a label diagram of the structure of lithium, and this is from your basic chemistry, right? So we have the nucleus here, we have the innermost ring, and then we will draw one more ring. Right, so we have 2 electrons here, and then we will have 1 more electron there. So remember, the amount of electrons is the same as the amount of protons, right, or the atomic number. So we have to label it, right? So this is the neutron, sorry, the nucleus. And in nucleus, we could say it has 3 protons, 4 neutrons. And this is an electron. Okay? In 4Ds, the activity of a sample of lithium decreases to 1/16 of its original activity. So they want us to define the term half-life. So you could get this definition from any textbook that you choose, right? So I'm not going to really give you a definition. You probably already have your definition that you want, right? But essentially, the half-life is the time that it takes for a radioactive element to decrease by 1/2 of its original value, okay? But you could choose whichever textbook you want and take your definition from there, okay? I'm not going to confuse you further by giving you even more things to learn, all right? Now they want us to calculate the half-life of lithium. It's very, very simple, right? So in 4 days, the lithium went to 1/16 of its original value, right? So how did we get from 1 to 1/16? So if 1 represents the original value, remember we have to decrease by half each time, right? So we went from 1 to a half of 1 is a half. Then we have to take a half of a half. So a half of a half is a quarter. Then we take a half of a quarter, which is an eighth. And then we take a half of an eighth, which is a 16th. And that is where we are, okay? So they said in 4 days, we went from the whole to 1/16, right? So we went 1 day, 2 days, 3 days, 4 days. So each time we reduced by half, it was a day. So therefore, the half-life is 1 day, right? Because in every day we went by a half. Okay, so the half-life, 1 day. Okay, now here's a new question. Calculate the energy given off in a nuclear reaction if the change in mass is that, and this is the speed of light here, right? The speed of light. Now everybody knows this famous equation, but not everybody know when to use it. The equation that we need to use here is E equals mc squared, right? This is the famous equation, and now we could actually use it. They want us to calculate the energy, that's E, in a nuclear reaction if the change in mass, that is m, and then they gave us the speed of light, that is c, okay? So this is essentially when the isotope gives off the radiation, its mass changes ever so slightly. Like we can't even really measure it that well, right? So we need special equipment to measure it, and this is an extremely small number, 0.2014 multiplied by u, and where u is this value here, right? So we have to use our calculators for it. So E will be this mass, will be equal to this mass, so 0.2014 multiplied by 1.66 by 10 to the minus 27, and all of that now is being multiplied by 3 by 10 to the 8 squared. Okay, so you definitely need to have your hands on a calculator in order to figure this one out. Okay, so let me just grab my calculator and I will calculate it with you. Okay, so 0.2014 multiplied by 1.66 by 10 to the minus 27, and I have a value for that. Right, but I'll keep that in my calculator, right? Because now I'm going to multiply that answer by 3 by 10 to the 10 to the 8 all squared, okay? if I write this out before, it will get kind of confusing with my calculator. I may not get the most accurate answer. Okay, so 3 by 10 to the power of 8 all squared. Alright, so I have my answer here. So let me show you how I worked it out. So the first thing I did was, I can't show you my calculator obviously, but what I did, actually, can I? No, I can't. Okay, so if I remember I did this in one swoop in my calculator. I'm just showing you what I got here, right? My calculator gave me this answer. Okay, but I did not put that equal and write it out and then cancel off my calculator and go and multiply by. I just did everything one time, right? And now I'm going to multiply that by this value. That's actually 300 million by 300 million, right? That's why we use scientific notation. You would get 9 by 10 to the 16, right? Because the 3 squared and the 10 to the power of 8 is also squared, right? So now we multiply both of them together. And our final answer, 3.00891 by 10 to the minus 10. That is your final answer. You have to use all your decimal places, okay? Because it's very, very minute measurements we're working with. Alright, that's how you get your marks. The final question is very easy. Here we have the particles in an atom. And we know the proton has a positive charge. The neutron has a neutral charge, that's why it's called a neutron. Neutral. And the electron has a negative charge. Okay, so for this element, it's called radon. Determine the number of each of the 3 particles. Now this is just like what we were doing before, right? So we have the atomic number here, 88, and we know the atomic number and the proton number is the same. So that's 88. And we now also know that the number of protons and electrons are the same. So 88 electrons as well. And finally, to calculate the number of neutrons, we simply take the mass number, which is 226, take it away from the atomic number, and we will get our number of neutrons. So we just put that in our calculator. Let's see. 226 minus 88, 138. Okay, very simple marks there. The next thing is to state one similarity and one difference between the isotopes of an element. So it's right there in front of us, right? The similarity, same proton number. No matter what, you have to have the same proton number or else the element will change, right? And the difference, so there's a difference in proton and neutron numbers. Okay, that's what makes it an isotope. Right, and again, you have the half-life definition where you could get anywhere, and I'm going to confuse you further. And we have a half-life calculation here. So the element thorium has a half-life of 24 days. and undergoes beta decay. Calculate the time it would take for 10 grams of thorium to decay to 1.25 grams. No problem. So half-life, right? So we are going from 10 to 1.25. So how many times do we have to have 10 to get to 1.25? Let's see. So 10 would go to 5. 5 would go to 2.5. And finally, 2.5 would go to 1.25. So how many times did we have the 10? 1, 2, 3 times to get to 1.25. And the half-life is 24 days. So each time it decreases by half, that is 24 days. Right? So if it's 3 half-lives, it's going to be 24 multiplied by 3, which is 72 days. That's how long it's going to take to decrease to 1.25 grams. And there we have it. That is a summary, a quick summary on radioactivity, radioactive decay, and also nuclear reactions. I hope you guys found this helpful.